Okay, it's my pleasure to introduce Emilie, also from College, and this her talk is some representations of the Virasoro algebra. Emilie.
Thank you. It's a pleasure to be here and to help celebrate Dan's birthday. I was here at UGA for a couple of years after my PhD, and I got to work with Dan and also be part of the bigger algebra group. And it was just a really wonderful experience, and I felt really lucky that that was my first experience after finishing my PhD. And what I didn't realize at the time, but I have since, is that I also had this bonus of being permanently adopted into Dan's mathematical family. And so even though many of the things that I've done have sort of taken me out of the direct orbit of what Dan does mathematically, I've still had his support in really meaningful ways throughout my career. And I've always felt like he's in my corner rooting for me. It's been really wonderful. So thank you, Dan, and happy birthday. All right, so I first learned about the Virasoro algebra as a graduate student, and I keep revisiting it since then and finding new interesting things to learn about it. So what I'm going to be talking about today are a few different families of representations for the Virasoro algebra. Some of them are really common. We just specialize for the Virasoro algebra, but I think there are nice things to say about them. And then another family of modules that take a different perspective on the Virasoro algebra, but end up having some nice connections to those more common families. All right, so let me just start out with the definition. So the Virasoro algebra is a Lie algebra over the complex numbers, and we have a central element Z, and then additional basis elements Ej, where J runs over all integers. So you can see the relations here. And as I said, Z is central, and then I'll point out that we've got a pairing between Ej and E minus J. That's when we pick up the second term, and that also E0 acts on any Ej by scalar multiplication. So we've got a nice root space set up there. And you can think of the Virasoro algebra as coming from central extensions of derivations on Laurent polynomials. So this is the identification that you can use to get that. And I'll come back to this at the end of the talk. And it also has structures that are familiar in lots of different Lie algebras. So in particular, it's got a triangular decomposition. So you can take E0 and Z to span a Cartan subalgebra, and then you naturally got these positive and negative pieces that are just spanned by the positively and negatively indexed basis vectors. So the Virasoro algebra comes up in a variety of different areas of physics. It comes up related to a lot of different other infinite dimensional Lie algebras, and it's just sort of a nice case study on its own. So that's sort of where I'm coming from on this. And if we were to start studying representations for the Virasoro algebra, might start with weight modules, or in particular highest weight modules. Right, so here I just have the definition of Fermat module, and because the basis vectors have the roots are just integers, you get that the weight spaces for a Fermat module are just going to be mu minus n for positive integers n. And so with this Fermat module, we might first. Do I need to change something?
Don't you want to pick up your video?
I should move over. So we've got a Fermat module, but what we really might want to know about our simple modules, so we could try to figure out what the simple modules look like from the Fermat module, or say something about the submodule structure for the Fermat module. So a good way to do this is to look at the Pavlov determinant. So for any Lie algebra with a triangular decomposition, you can define a bilinear form on it that's going to pick out highest weight vectors or pick out elements of a submodule, and it'll be orthogonal on different weight spaces. And so it makes sense to look at how the form acts on a given weight space, and then we can use a determinant calculation to pick out degeneracies in the determinant are going to tell you when you get something in a submodule, right? So that's this Pavlov determinant, which we have nice formulas for this for, say, semi-simple finite dimensional algebras. And it turns out you can get a maybe not so nice formula for the Virasoro algebra. So there's a lot of things going on here, but again, what we care about is when the determinant is equal to 0. So this really what really matters here is when these curves C
Rs of mu are equal to 0. So for what R and S, for a given mu, for what R and S do you get, those curves are equal to 0. And so those curves, C, they're polynomials in the weight. So here, I think I wrote this on the previous slide, but I'm thinking of E0 as acting by H and Z is acting by C. So the curve you get at the bottom, I've written as polynomials in H and C. And certainly you could check when these are 0, but as written, they're not super informative about what the submodule structure might look like. But the key thing here is we were interested in these integer pairs R and S when it's equal to 0. And so if you instead focus on those, you get a nicer picture. And it turns into a really nice description of what the submodules of M look like. Right, so in fact, those curves factor into 4 linear terms in terms of R and S, and then there's symmetries between those. You can really pick any of them to focus on. And so what we want is integer solutions, and the equation of a line is going to pass through either no integer solutions or one integer solution, or infinitely many integer solutions. And that turns out to give you the structure of submodules for these Verma modules. So I'm going to show you that picture. All right, so again, if the line doesn't pass through any integer solutions, the Verma module itself is simple. It might pass through one, in which case you get one submodule, another Verma module, or you might get these infinite chains. So you can see that there are 2 types of infinite chains of embeddings that you get. It might be some strict chain, and that happens when the corresponding line crosses an axis in an integer solution. And if not, you have to look a little bit more to get additional submodules. And so you'll see these R and S tilde. So there's an additional line that you have to consider in that case. And so having this description of what the submodules, oh, and I should also say that these pictures, so notice that for the type 3 and type 4 blocks that you get here, there's a maximal element. And there could also be the flip of all of these chains of embeddings that you get where you have some minimal element, right? But you have these infinite chains in both cases. Okay, so having this description of what the submodule structure of a Verma module looks like then allows you to answer all sorts of questions, or at least get started on all sorts of questions about what highest weight modules look like for the Virasoro algebra. And I'm not going to chronicle all of those, but I did wanted to mention one. This was something that I worked on with Brian Bowe and Dan while I was here at UGA, that you can describe extensions between, here the L's are simple modules, so you can describe those extensions really nicely in terms of this picture, that it's going to be in terms of the relative positioning of mu and lambda on a given chain of these embeddings. And then we also looked at a variety of other related questions there. Right, so a lot is known about highest weight modules for the Virasoro algebra. And we might ask more generally about weight modules. And again, people have been able to say a lot in this case. So simple Harish-Chandra modules, these are going to be weight modules that have finite dimensional weight spaces. And so it turns out these only come in a few flavors. They're either highest weight, lowest weight, or these intermediate series modules. So the intermediate series modules are going to be twists of the natural representation on the Laurent polynomial. So you end up with all one-dimensional weight spaces, but it's going to extend infinitely in both directions. And sometimes you have to quotient out by one of those weight spaces to get something simple, but that's essentially what it looks like. Yes, yeah. And you can extend this a little bit. So in fact, if you have a simple Virasoro module that has any finite dimensional weight space, then all of them have to be finite dimensional. And so it just puts you back in the classification that Nacho gave already. And then the next step would be to think about infinite dimensional weight spaces, which seems like a much bigger puzzle to crack, but there are various families of weight modules with infinite dimensional weight spaces that have been constructed and proven to be simple. All right, so all of this is again, we're looking at weight modules for the Cartan subalgebra that I defined. So we've got some nice action of the Cartan subalgebra spanned by E0 and Z. If we were thinking about other interesting modules, we might just pick another piece of the triangular decomposition and wonder what modules look like if there's some nice action for those. So let's pick the positive part. And what might we mean by a nice action of Vir plus? So as a starting point, we might just want to look at things that are induced up from some simple Vir plus module. And again, you might start by looking at one-dimensional Vir plus modules. So here eta is a Lie algebra homomorphism from Vir plus into C, and then we can define a one-dimensional module for it, and then think about the modules that are generated as Vir modules by one of these one-dimensional Vir plus modules. And this idea was the original notion of a Whittaker module. And I'll just list one of these, which now gets called the standard Whittaker module. Typically, we could just take a one-dimensional Vir plus module and induce it up to the full module. And this is notation I'll use later on, so that's why I wanted to introduce it here. But these sort of don't make up a nice category on their own, so maybe the right category to look at here is Vir modules where Vir plus acts locally finitely. Right, so Whittaker modules, they were first studied extensively by Poston, and he described what simple Whittaker modules look like for finite dimensional semi-simple Lie algebras, and then there's sort of a cottage industry of taking that same construction and using it for a variety of other Lie algebras, including the Virasoro algebra. And then Mazurchuk and Batra gave this category definition here as a way of trying to gather together all of these different attempts to describe Whittaker modules in different settings. And so they had a very general setting in which to look at Whittaker modules and Whittaker categories. So they actually defined these Whittaker categories W, and then they showed that it decomposes into blocks according to this action by Vir plus. So we can label the blocks by Lie algebra homomorphisms Vir or eta from Vir plus into C. Right. And they gave a construction of simple modules by identifying one-dimensional Vir plus modules and a completion of the module. So they could do this for any choice of eta and highest weight mu. But in the general setting that they were looking at, they couldn't prove that those were all simple modules for a given Lie algebra setup. And Matt Anders and I looked at this for the Virasoro algebra in particular, and we basically showed that the modules constructed by Batra and Mazurchuk do give you all of the simple modules, although we had a more concrete description of what they look like. So the zero block for W, this is where this is going to include highest weight modules in category O in general, and in that case, it turns out that the simple objects are just going to be the simple highest weight modules. And then for non-zero eta, we can get simple modules by taking a quotient of the standard Whittaker module, where you let Z act by a scalar. And it turns out that it's in many different settings, the center of the universal enveloping algebra of the Lie algebra seems to play an important role in describing what the Whittaker modules look like. So it comes up here in defining these simple modules, but then also if we restrict to modules in this category that have finite composition length, so that's what the F represents there in WF, then the action of Z really describes what's happening in the modules overall. And so you can decompose those blocks further into the action of Z, and then you just get basically strings of the unique simple module put together. And you can determine the composition length fairly easily from what's happening with the action of Z. All right. And then, so all of this is this construction for the Virasoro algebra in the positive part you can also do for subalgebras of the positive part. And so various people produce simple modules in that setting, and Mazurchuk and Zhao gave this unified theory of all of this, where they could look at any one of these positive parts. So here we're just taking, rather than sort of cutting off the algebra, making a submodule starting at 1 and going off, and start at any along there, and we get a subalgebra, and then you can do a corresponding construction, and you get the simple modules look very similar to this. So they're going to be determined by some homomorphism eta on that Vn, and then also the action of Z. All right. So going through all of this, we've got the weight modules and the Whittaker modules. Both are relying on, are coming from the triangular decomposition of the Virasoro algebra, and there's lots of nice things that you can say about the modules there. So this brings us to the final family of modules that I wanted to mention. And as I said before, think of it as we're sort of ignoring the triangular decomposition and going back to the fact that we can think of the Virasoro algebra as central extensions of these derivations on the Laurent polynomials. So this is the identification that I put up before. And so if I take just an arbitrary polynomial, I can then associate it with an element of the Virasoro algebra. So, and I can associate it with a whole family of elements where I'm basically taking the polynomial and translating it over to the corresponding element in the Virasoro algebra, and then we can do some kind of shift by tj, however we want. And then if we take the collection of these and add in the central element, you get a subalgebra of the Virasoro algebra. And what's potentially nice about these is that they have finite codimension, right? So the codimension is just going to be the degree of the polynomial that we use to construct the subalgebra. Okay. And in fact, if we look at, no, J is going to run over all integers to get a subalgebra. Yeah, although I'll come back to that later, that we can restrict it to be positive and we still get a subalgebra. Yeah, so if it turns out that you can show that the subalgebras of the Virasoro algebra of codimension 1 are going to be exactly these polynomial subalgebras. So we get all of them by this construction. I don't know what happens in the general case, but I think there's been some, a recent paper by Petikoff and Sierra have been able to say something about what the finite codimension subalgebras of the Virasoro look like in general. All right, so we have a subalgebra. Again, what's the standard thing to do? We'll take some nice small module for the subalgebra and induce it up to the full algebra and see what we get for modules. So that's this construction here. I can just take any Lie algebra homomorphism from Vir F into C, and then I get a module, a one-dimensional module associated with that, and then I induce it up to the full Virasoro algebra. All right, so I want to know when these modules are simple and anything else I can say about their structure. But as a starting point, I need to know what these mu look like, and it turns out there's some nice descriptions of those that we can come up with. So if I'm starting out with some polynomial f, can write it in terms of its distinct roots, and then for any Lie algebra homomorphism on VF into C, it's going to be defined in terms of a set of polynomials where there's a polynomial associated to each of the distinct roots. And then we get homomorphism exactly when the degrees of those polynomials are less than the multiplicity of the root. Right, and it turns out that this description is useful in determining the simplicity of the induced modules. All right, so this is that description. So first I'm writing it just in terms of polynomials f that have a single distinct root. So in that case, the homomorphism u is going to be associated with just one polynomial p. And then the induced module is simple exactly when the degree is large enough. So remember, the degree of the polynomial has to be less than n. And so this is really saying it's got to have degree either n-2 or n-1. And then the module is simple in that case. And the idea of sort of why you get these two cases is that you can have a non-trivial action of either E0 or E2 in there, and that sort of gives you the simplicity. And if you had a polynomial that had degree less than n-2, then you can take you can find a quotient of this module that's going to be isomorphic to one of these polynomial subalgebra modules for a smaller degree polynomial. And so you can always find a simple quotient of these, and you can describe what the composition series looks like. Okay, and then for the general polynomial f, we can take that induced module and write it as a tensor product, one term for each of the factors. And that's what we get there. And then the induced module is going to be simple exactly when each of the tensor pieces are simple. And the idea of the proof of this is that if you look at the polynomial or the subalgebra corresponding to f, it's going to be the intersection of the subalgebras that correspond to each of the distinct root polynomials. And so you can use that then to break up this module over the tensor product. That the subalgebra is the intersection acts in a nice way to allow you to do that. All right, and so these modules, they're not going to be weight modules, they're not Whittaker modules, there's some new family, but I said at the beginning that there's some nice connections between these and some of the modules I talked about at the beginning. So I wanted to lastly share a little bit about those. Okay, and the first is not a connection to the Virasoro algebra modules, but actually to SL2. So the Virasoro algebra has lots of copies of SL2 in it. This is one of them. We can take the span of E-1, E0, and E1, and I'm thinking of these as mixing up with the standard basis E, H, and F. And since it's a subalgebra, we can think about, well, how do modules for SL2 relate to modules for the Virasoro algebra? And in general, it seems like it's probably not anything interesting because SL2 is very small with respect to the Virasoro algebra, and so I would expect Virasoro algebra modules to look really big as SL2 modules and not necessarily to have something interesting to say about them. But in the case of these polynomial subalgebra modules, because the subalgebras that we're inducing from have finite codimension, maybe there's some hope there of something interesting coming out of it. And it turns out there is. So this describes what happens when we take those polynomial subalgebra modules and restrict them to SL2. We get copies of these familiar induced modules for SL2. So M here I'm using to represent the Verma module. W is going to be the standard Whittaker module, but for SL2. And then X is another induced module where I'm inducing them from the simple module for H for the Cartesian subalgebra. So you're going to get infinite in both direction weight spaces. All right, and the gammas that I have written there, those are automorphisms of SL2. So they're going to permute the various subalgebras of SL2. So in particular, for our Verma module, we're reducing this up from some Borel subalgebra, and so that permutation is as we let lambda vary, it'll permute over all possible Borel subalgebras, and the same thing for in case 2, it'll run over all of the nilpotent subalgebras that we might choose, and so on. And so this pairing or the relationship that we're getting here on the left side, these are modules that are induced from a finite codimension subalgebra. So in the first case, that polynomial has degree 1, and so the corresponding subalgebra has codimension 1 in the Virasoro algebra. And then on On the right side, the Verma module is going to be induced up from this Borel subalgebra, which also has codimension 1. And so you're getting sort of a matching between the codimensions on the two sides. And then the same thing in the other cases. So in case 2 here, we have a polynomial of degree 2. So it's coming from a subalgebra of codimension 2. And then the Whittaker module is we're inducing up from a module for just the nilpotent piece, which also has codimension 2 and so on. So you get this nice correspondence. And then again, these gammas, they're going to be permuting all of these subalgebras, and so you're basically getting all possible induced modules for SL2 are showing up as restrictions of these polynomial subalgebra modules. Right. And then one other connection that I wanted to make between these and the modules I talked about at the beginning. So there we can define other subalgebras rather than letting J run over all possible values. We can cut it off somewhere and get a submodule. And so if we cut it off at any value of n bigger than or equal to n-1, that's when we get a submodule, right? So define these new subalgebras, which are the restricted polynomial subalgebras, B and F, where F is still representing some polynomial, and then N is where we're cutting things off. Right, and notice that these are the intersection of one of the regular polynomial subalgebra modules, and then just one of these BM, which came up earlier when I was talking about Whittaker modules. All right, and then we've got a subalgebra, so why not define some induced modules for it? So that's what these V, F, M are, just inducing up from one of the restricted polynomial subalgebras instead. So again, what do these modules look like? So we get a nice tensor product decomposition. Now we can break this up in terms of just a regular polynomial subalgebra module, and then something that's induced from these subalgebras, BM. And then the tensor product is going to be simple exactly when each of the pieces is simple. And there's some decomposition of the homomorphism mu here as well to go with each of the pieces. All right, and so now these induced modules are familiar modules that we get. So in the case that m equals 0, this is just a standard Verma module, and we know a lot about what those look like. In the case m equals 1, this is corresponding to a Verma module where E0 acts by 0, and so you get a standard quotient that you can take there where you cut out the first weight space. And then the induced module you get from BM is going to look like that quotient of the Verma module. Right? And so in general, Verma modules are going to be simple most of the time, although we have that picture of what they look like. And these quotients, again, this is corresponding to E0 acting by 0. They're going to be simple, except when you're in that case 4 picture that I showed earlier. And then for n greater than 0, you end up with the simple Whittaker modules. So m equals 1 is where you get the Whittaker modules that I more formally defined. And then when m is greater than 1, you get the generalizations that Mazurchuk and Chow came up with. Okay, so these we can use those earlier descriptions. They show up here in a nice way for these new restricted polynomial subalgebra models. All right, thank you.
Questions or comments?
I think that is that how do you define XJF and J is negative? We just switch things.
Oh, so it's always going to be a translation to the elements of these polynomial subalgebras. So yeah, so we can think of it as just if we're associating these elements by to some Laurent polynomial, we can still multiply by tj when j is negative.
Any other questions or comments?
I should make a comment. So I actually wrote my thesis in this area also. How much of this actually extends the other realities of quantum tests? Like, if you take it without.
I don't know.
Should be able to-
Right, yeah.
Similar to what Dan asked, what about the toroidal algebra? Is there a similar theory for toroidal algebra? Of course, the central extension there is very tricky.
Right, yeah, so there's nothing else that I know of, but I don't see a reason why it wouldn't make sense to think about it.
Maybe you have said it already. So, is the critical category, highest weight category, since it's CPS or any chart plan, something?
I didn't understand the question.
So, is the category, highest weight category was definitely chart by category, something like that?
I don't know.
It's small, so.
I guess similar to that question, do some type of like a PGD resolution in these contexts, like for example, the setting of these Virasoro algebras for this group,
For Whittaker modules,
in the Wiesner category.
well, I mean, for.
There is not much bias there. I don't think that there will be.
Yeah, I mean, I don't know what, you can't, I mean, you can write down, you can do it for category O, even though you don't have a file group, but I don't know what it would be for Whittaker, in the Whittaker categories. You do get, and when you have objects of finite length, you get really nice descriptions of what they look like in that case, but I don't know what the more general objects, I don't know anything about what they look like in the Whittaker category.
There's very small bias, but really not much.
Anybody else? You sure, don't change last questions now. That's the one last question. So, come on, don't you know anything about the characteristic P? Anybody has done, that question.
No, I mean,
Because so many people, positive characteristics are very positive, so. Not positive.
But you see, the real determinant is so very easy in the range. Because the coefficient K minus L.
That's what the tan thing is, right?
So like in Joker's, you could look at the good algebra. So the finite dimensional, simple real algebra. And it turns out that the SL2 that we presented is very, very important. Because you can actually show that the distributed development has only one block. And use that SL2 actually. So there's a lot of things.
And can you go to the slide?
Yeah. maybe.
It is a good. You have a transfer product from.
This
Yes.
one?
What are the sample charts? Or is there a sample chart in the?
It's always 0.
Oh, zero.
Yeah,
Okay.
yeah, that you can show for these. For any homomorphism into C, it has, yeah.
So big, in this case, sample chart is always zero.
Yeah, which shows up too in this later.
what happens for non-zero circuits?
Well, you don't get one-dimensional one-dimensional modules for the subalgebra in that case.
No more question. We'll break and come back.